Okay, this video is the second part of thermodynamics. This is quantity of heat and heat transfer. So I will be able to understand specific heat, heat capacity, and the transfer of heat. We're going to take notes from a video, discuss with our groups, and conduct experiments. So the effect of heat on temperature depends on the quantity of matter heated. So the same quantity of heat is applied to each mass of water in the figure. The larger mass experiences a smaller increase in temperature. So basically, if we have a larger mass, it's going to take more heat in order to heat it up. The heat capacity of a substance is the heat required to raise the temperature a unit degree. So in lead, all of these at 100 degrees centigrade, it takes 37 seconds for lead, 52 seconds for glass, and so on. And iron is at 90 seconds. So heat capacity is based on time to heat from 0 to 100 degrees, which has the greatest heat capacity. So in this case, the one that takes the longest has the greatest amount of capacity that it can hold, so it would be iron. Alright, and then actually they're in order from greatest to least, so copper, aluminum, glass, and lead. So all at 100 degrees centigrade placed on a paraffin slab. Iron and copper balls melt all the way through, others have lesser heat capacities. And because it has a greater capacity, it gets hotter and hotter compared to the other ones. So this is how we determine specific heat capacity. The specific heat capacity of material is the quantity of heat needed to raise the temperature of a unit mass through a unit degree. So basically the amount of heat it takes to raise it 1 degree. So specific heat over the mass over time. So in this case, water is 1 calorie per gram or 1 BTU per pound Fahrenheit or degree, or 4,186 joules. And then in copper, we have C equals 0.094 calories gram degrees, or 390. So these are all different specific heats in order to raise 1 unit mass to 1 degree. So how much heat is needed to raise 1 kilogram of water from 0 to 100 degrees centigrade? So we are given 1 kilogram is 1,000 grams, and it's also equal to 0.454 pounds. 1 pound is 454 grams. So for water, C equals 1 calorie per gram per degree, or 1 BTU. So the heat required to do this job is 10,000 calories, or 10 kilocalories, 39.7 BTUs, or 41,860 joules. So we're going to read the problem carefully and draw a rough sketch, make a list of all given quantities, determine what is to be found, recall applicable law, formula, and constants, and determine what was to be found. So here's our example. We have 500 gram copper coffee mug is filled with 200 grams of coffee. How much heat was required to heat the cup and coffee from 20 to 96 degrees centigrade? So draw the sketch of the problem, our lovely copper cup. I don't really know who's going to drink from a copper coffee mug, which is kind of nasty. But anyway, list the given information. Our mug mass is 0.5 kilograms. Our coffee mass is 0.2 kilograms. Our initial temperature is 20 degrees centigrade, and the final temperature is 96 degrees centigrade. So we're going to list what is to be found. So we're going to list the total heat to raise the temperature of the coffee or water and mug to 96 degrees centigrade. So again, here are our givens. So we're going to recall the applicable formula or law. Heat gain or loss is Q equals MC change in temperature. So decide that total heat is that required to raise temperature of the mug and water combined. So we have MC change of T plus MC change of T. and the specific heat of copper is 390 joules per kilogram centigrade, and then specific heat of coffee, which we're going to say is water, is 4,186 joules per kilogram centigrade. So all we're doing is popping these into the equation. Copper is 390, 490, so water is 0.2 kilograms times the specific heat, alright, which is C, and then the change of temperature from 20 to 96. So 96 minus 20 is 76. And we have the cup, 0.5, 390, 76 again, and we add them together, it gives us 78.4 kilojoules. Okay, in which case this would be 78,400 joules. Okay, so notice that they went to kilojoules here. So a word about units. The substituting units must be consistent with those of the chosen value of specific heat capacity. So we have this ugly thing with joules, kilogram centigrade, and we have 1 calorie per gram centigrade. So the units for Q and M have to just be consistent as long as that's what you have. So if you use calories, then your Q must be in calories. So you have to pick between the two things here. Conservation of energy. Whenever there's a transfer of heat within a system, the heat lost by the warmer body must equal the heat gained by the cooler body. Okay, so it's all very Newton-esque right here. So the hot iron, if I put in the cool water, that means the amount of energy transferred to the water should be equal to the amount of heat that was given. So a handful of copper shot is heated to 90 degrees centigrade and then dropped into 80 grams of water in an insulated cup at 10 degrees centigrade. If the equilibrium temperature is 18 degrees centigrade, what was the mass of the copper? So we are dealing with specific heat of water, specific heat of copper. Okay, so we have the shot right here and then that. And then the mass of the water was 80 grams. The temperature of water was 10 to start, and then the starting temperature of the shot was 90 degrees. So we're taking this MC, change of T, MC, change of T on both sides. So we set them equal to each other. So we have 80 grams times 390, and then we have the change in temperature, 90 minus 18. Alright, and we have the same thing on the other side, and all we're doing is trying to solve for this over here, the mass of the copper. And every time, if you see here, the temperature differences have to be high to low, so you're never going to get a negative. So heat lost by the shot equals heat gained by the water. Our water is 18 minus 10. Our shot is 90 to 18. Okay, because it wants to get to equilibrium. All we do is we change everything, and the missing mass that we have is 95.4 grams. Because all we did is multiply these, and then again we want this variable by itself, so we had to divide by these two numbers. So, change of phase. When a change of phase occurs, there's only a change in potential energy of the molecules. The temperature is constant during the change. So, solid changes to liquid to gas, and it goes back and forth based on the temperature change. So, when solid, from solid to liquid, is fusion, which is seen as Q equals MLF, and then liquid to gas, vaporization, Q equals MLV. So fusion, vaporization, condensation, latent heats, evaporation, freezing point, melting point, all important terms. So first law of thermodynamics, the total amount of energy in any closed system is constant. Alright, energy loss is equal to energy gain. Second law of thermodynamics, in a closed system, energy flows from hot to cold. And we've already kind of covered these things. So whether we do heat, work, mechanical energy, chemical energy, it's going to go from high temperature to low temperature. And then the zeroth law of thermodynamics. We have already discussed the zeroth law and included here for completeness. So if object A is in thermal equilibrium with object C, and object B is separately in thermal equilibrium object C, then A and B also have to be in thermal equilibrium if they are placed in contact. And our last thing, entropy. The total entropy of the universe increases whenever an irreversible process occurs. So the total entropy of the universe is unchanged whenever a reversible process occurs. So, since all real processes are irreversible, the entropy of the universe continually increases. If entropy decreases in a system due to work being done on it, a greater increase in entropy occurs outside the system. Okay, so this is just a small bit of entropy. Video's done, but there's a bunch of vocabulary to get.